Hey everyone, it's Noah here. I am glad that you're joining us today and welcome to the sixth live stream. This is a live stream part of the machine learning series, and what we're going to do today is just play around with different machine learning technologies and algorithms and hopefully learn something along the way. I want to recap that what we saw on last week's video was a brief introduction to TF records. So I was preparing some slides to what TF records are and a really small sample. As a recap, TF records are the standard on how to create data sets in a way that can be streamed fast to TensorFlow. And we're going to see some more stuff today. I would encourage you to take a look at the playlists that are already on the YouTube channel if you want to see what we've gone through already, and to join the Discord community in case you wanna join us and have a chat. Before I continue, I would like to say, does this sound good? Is everyone seeing me okay? And does the sound feel good? Hello to Luli and Jose Luis Garcia del Castillo for connecting. And if everything sounds good, we're gonna get started. All right. So I have this little outline here. This is something I just try to do before every live stream, just to see what we're gonna cover. In past live streams, you might have seen that I have some other notes, and there is a huge list on things that I have taken a look at that I would like to look at in future videos. So for today, what I thought is that I will introduce you to a few links that I've been thinking about, and then dive into the content that we're gonna take a look at today. So I've discovered or seen the FastAI library. I didn't really know it was a helper library. Let me just get out of here. It's a library that simplifies a lot of the training steps and process to use neural networks. So I'm taking a look at this and trying to see if I use some of the functions here. It seems like some of the Google TensorFlow tutorials use FastAI's helper methods to streamline the way that data is modified and edited, and how networks are trained and are used for predicting on data. I also, so here I think this is the course in which I actually learn about FastAI. I think I'm not too sure. So this is a course, it says here, written by a Googler, but if we go to the end, we can see it's written by Martin Gorner, and I haven't gone through the entire thing. I've just skimmed through it, but it's a really good introduction to neural networks and convolutional neural networks to classify, and many of the important concepts on machine learning. I don't know, you can see here neural networks, layers, learning rate decay, dropout, overfitting, convolutional networks, and a lot of stuff, right? So if we go back to our notes, let me just leave. Yep. Stylegun. I'm also taking a look at Stylegun. So I'm trying to get a hang of how to easily train. So I've gone through the process of seeing how to prepare Runway to train with your own custom data set and custom images. We also can use Colab to train. Google gives you GPUs and TPUs for free, as you might know. And just by training this little, let me see if I can take a look at a little experiment that I've done. I just trained for 2.5 hours on what's called the cartoon set data set, and by training for 2.5 hours, it got to this. It's a bit weird, and we'll be able to see more of this in future videos. But what this shows is that the what's called the Flickr faces high quality data set, that is 1024 pixels by 1024 pixels, was trying to get adjusted to these cartoon-like faces. I imagine that if we keep training, the data will be looking more alike to the actual data set that I was training with. This is a sample data set that notebook that I was showing will provide you. But what I'm looking for is to train with my own custom data sets, not with that test data set that they were showing. Let me just unzip this. Let's see if I can unpack this file so you see the actual data set which was used to train those cartoon faces. Yeah, and this is a notebook. If you go to the Stylegun to repo on GitHub, you'll find that link. That's on the Discord channel from last week, I think. And these are the data samples of that data set, right? So from the Flickr faces HQ data set, yeah, from, I don't know if it's this one, but it's similar to this one. So it's just faces of people, and you can use that as a checkpoint to then retrain with your custom data set, and it takes hours to train instead of days or weeks. All right, let's see one more thing here. All right, and well, I'm not gonna talk about Amazon recognition. That's something I've also taken a look at. What I wanna say right now is just remember that we're creating a community and on Discord, and this entails not only machine learning but also the projects I do with podcasts, at Getting Simple, sketches, writing, and anything that has to do with creativity and data, art, and design, and using code for it. So yeah, I'll invite you to join me and to join some people. There's some people already there. We've been chatting, and I expect that this will be welcoming you and welcoming more people as the weeks go by. All right, and we had the slides for last week, and you can see the video for last week, but we'll probably expand on this TF Records presentation in the future. So the first thing for today, create live streams playlist. So we have a bit of a mess on the YouTube channel, so I wanted to take these moments to make sure that that's tidy. So you can see that the machine learning series live streams are merged here, and we have the live streams, we have videos between, and then the live streams are also here. So what I'm gonna do, I'm going to just create a new playlist for that purpose, to have all the live streams stitched together so they're easily accessible. All right, where can I do that? Okay. All right, so we'll just go here. Playlists, new playlist. Right, live, we'll just call it live. All right, and we're just going to go probably here. Well, I think I can go here to videos and past live streams. Yep, all right. New playlist. Oh, that's the current one. Okay. Right, seems like I might be. And that way, what we're doing is that we're bringing the background noise I was recording All right, mission failed. I don't think this computer can hold all those tabs open at the same time. All right, so with that, I will probably just do that offline, but what we'll do is I will have all the videos that have to do with the live stream just on the live streams playlist, so they won't be mixed around everywhere else. All right, so let's get started then. So we had this other link here, so also gonna show that before we get started. So you can go to gettingsimple.com/record or ask. They both take to the same place. And if you want to ask me something, anything that has to do with the podcast, has to do with the live stream, machine learning, I'll try to do my best and answer your questions. So you can just click here on start recording. So I will do something like that. You can see that this is now recording. So let's stop it and reset. And you will just say, "Hi Nono, my name is Nono, and I just want to ask you, why do you do this project?" or whatever question you might have. Thank you. And then, you'll put here your name, put here your email, and, this note, let me just make sure that we're not feeding the audio here. All right. "Hi Nono, my name is Nono, and I just want to ask you." Yeah, and you would just press send, and that will come to me. I'll receive an MP3 with your question, and I'll be able to answer that. All right. So for the people who are connected right now, can you hear me right? Can you see me fluidly? Am I slow, or how is it working? Okay. Okay, so we are gonna take a look at these tasks. So if you go to tensorflow.org /tutorials, you're gonna be able to see a bunch of ready to run tutorials. So that means that they have I think most of them are in TensorFlow 2.3.1, the latest version already. And they're from beginner to advanced, and there are many different ones that you can learn. So from image classification to conceptual understanding of how to save and load models, what overfitting means, how to load and process data, customization, and distributed learning, object detection, image segmentation, convolutional neural networks, text, audio, a lot of different things. What we're going to see today is one of the basic examples on image classification. What would be boring, right? We could finish here if you just open the notebook and run it, which is something that we can do and are going to do. But what we're going to do is go step by step, covering everything that is on this notebook, and that is really well explained here, to understand the underlying concepts, what is this doing, and understand how we can save our model and then use it in a different environment, maybe in ML5JS, in TensorFlow.js, in Runway, on a Python application, on our server, whatever we want to use that. So as I mentioned before, so we can run this directly. So you can see if I click here, I get a runtime allocated. That's a Python kernel that's going to run on the backend of this Colab notebook provided by Google. And if we look here at, we go to runtime and then change runtime type, we can choose here a GPU. And this is something we need to do before getting the kernel allocated. You see that now we are allocated a kernel that has a GPU reserved. First thing, we can modify this here, so we could add here something really silly here, and we can run to see what TensorFlow per version we're using. We're using 2.3.0, and we could press Shift Enter to execute each of these cells, and here it tells us we have 2.3.0. If we click on Run All, this is just going to run the entire notebook, and what it will do is just go through the entire exercise to download the data set, format it, train a neural network to recognize, and then test the model. Not sure how long this takes to train, but it's already gone through a lot of these steps. So the model is built here, and we're gonna take a look at that quickly. So yeah, and the model trains really fast. This is a really simple neural network that only has, I believe, only has these 3 layers, and that is going to finish training right now. Okay, trained, so accuracy is 88%, as you can see here. Let me move myself, and what we can see here, okay, and then the model is being used here to do an inference on a new set of test images, and it's gonna give us a set of predictions. So we run here predictions. We can see that we have one prediction per image. Does that work? Yes. Jean-Marc, is that a problem with where you're connecting from, or is that the stream is not something that you can see? Okay, so for each image that we're testing, so we can say here print length of predictions. So there are 10,000 test images, well, maybe, and we're just printing the first one and seeing what class it is. All right, so let's get started from the very beginning, and what we're gonna do is that we're gonna create a new notebook. So we're gonna start clean, and we're gonna start step by step. Hopefully we can finish this today, otherwise we'll just continue next week, and we'll close this for now. Just try to close as many things as possible for this not to go slow. I'm just gonna reply here. All right, where were we? So we have here limited screen space, so I'm going to be sharing here, and again, okay, so we're gonna call this basic classification. So this is live 6, basic classification of what this is called fashion MNIST. All right, and I'll go through a few concepts. So the Google team here, what they're trying to do with this tutorial, let's zoom in once more. So what they're trying to do with this tutorial is to use the this fashion data set as the MNIST dataset was being used before, as a test dataset that can be used to train neural networks and measure their performance. The MNIST dataset was a famous, well, is a really famous dataset that had a lot of handwritten digits like these ones that Jan LeCun used to train LeNet, a CNN or a convolutional neural network that was able to classify individual digits on checks on the US, I think. And I think this was in 1998. Yeah, so 1998. And they obtained a really good accuracy. At the time, they performed normalization on this dataset, which means that each number was centered and resized to the same image size, 28 by 28 pixels, and they were labeled. And then the neural network was able to recognize with sort of great accuracy. Today, the networks are better, but the big breakthroughs in convolutional neural networks all were based in this initial work. Something like AlexNet and VGG and ResNet. Well, ResNet is a bit different, but GoogleNet as well. GoogleNet actually is called GoogleNet. That has this wink here, LeNet, because it's an augmentation of the work of Jan LeCun. All right. So, get back here and let's get started. So, the steps are already outlined here. We have to import the fashion MNIST dataset. We have to look at that data, see what it is, try to understand it, pre-process it, then build a machine learning model that is a model that is just going to be, it's just a set of layers inside of a neural network. And then we have to train it. So I don't know if this expands. Yeah, we have to compile the model, then train it, then feed the model with test images that the network hasn't seen before during the training process. And then we're going to evaluate the accuracy to see how well the network performs. We're going to make predictions and verify them and use the training model. This seems like a lot to cover in 1 hour and a half, but we'll just see where we get to. Again, you can see the source code on GitHub, run the Colab notebook or download the notebook to run locally on your machine. For me, I'm going to allocate a GPU here to make sure that the training is fast, and I'm going to connect to it. See if we get it allocated quickly. That shouldn't take more than a few seconds. And we're just going to see here, for instance, we can take a look at the Python version, and we can import TensorFlow as TF and take a look at the TF version. On previous videos, we've taken a look at what this Google Colab environment is. It's something called a Jupyter Notebook, and you can go back at other videos to take a look at that, or just try to learn that somewhere else. We can go in more depth into that if you want to. So these are the dependencies that Google requires. So this tutorial depends on. So we're just gonna put them all here. So we import TensorFlow, we import NumPy as MP, that's a scientific library, and we import matplotlib. They have an auto completion here for rendering images and charts and things like that. All right. Again, we print the TF version. We can put that in the same cell. All right. That's it. So TensorFlow and TF Keras, and these are helper libraries. All right. This guide uses the fashion MNIST dataset with 70,000 grayscale images in 10 categories. The images shown individual articles of clothing at low resolution, 28 by 28 pixels, as seen here. Right, so I already showed that before. So we have all of this. This is just a small sample per category. We're getting 3 rows, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes, and we have here some samples of the classes, maybe 50 or something, or 100 images. I don't really know, but this here is the data set that we're going to be using. All right. And how do we get that? So this is, as they mentioned, is intended as a drop-in replacement for the classic MNIST dataset, the one I just showed. And it's used here as a Hello World machine learning dataset. Contains, the one that we've seen contains handwritten digits, blah, 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 blah. Okay, so we're going to use 60,000 of those images as training dataset. That's to train the network, and 10,000 images to evaluate how accurate it is. Again, what this means is that you get all your data set, in this case 70,000 images, and you take 60,000 and say, okay, I'm going to use this for training my model, and then you use 10,000 that you're not going to use to train your model to evaluate how well it performs. That would be as if you had 100 pictures and you say, okay, I train a neural network with 80 of these pictures that are representative of my data, but then I use the remaining 20 to check whether that model that you've trained performs well on images that you haven't used for training. Because if all the data you test with are on the training set, you already know what categories those are, and the network already has been able to learn about them. So you want to find new samples that haven't been introduced on the network yet to see if it works properly, because that's a real life situation. You will get images that the model hasn't seen before. Maybe you take a picture with your camera, or you download something from the internet, or somebody just feeds an image they have on the computer, and your network has to perform well on it. It needs to be the same kind of data, but not data that the model has already seen. All right, how do we get this data set? So Google, TensorFlow, Keras, and other libraries make it really easy to download these data sets automatically. They already have what's called helper functions to do this inside of their library. So there is a function here that's like fashion MNIST load data, and if we run that, what we're doing here is we're deconstructing. Let me just write it here. So train images and train labels, and test images, test labels. Fashion MNIST load data. This here, so this method here returns probably, I don't know, maybe a tuple. So it will return something like this, and then X is something like that, and Y is something like this. So probably if we go into this method, it's returning something like this, I will guess, or maybe something like this, I'm not sure. But here what we're doing is deconstructing that variable. So when we load the data, this data set already gives us the training images and their labels, so what class they belong to, and the test images and their labels. The images and what labels, so what classes those images belong to. All right, let's see. So if we run this, I will expect, this has to download data. This data set is probably not too big, but it will take some time to process, and it's done. So now we go into train images. We can see there are a bunch of tensors there, and first thing we can do, train images and count it. All right, so we have 60,000 of those images. Let's see, for instance, on train images 1, so this is the first one. Let's try to see the shape of this tensor. So it's a 28 by 28 tensor, or well, in this case it's just an array, so it doesn't, well, let me just see. Right, so this is an array, so it's not even a TF tensor. So if we were to do TensorFlow convert to tensor on train images 0, we will get a tensor. Okay, so shape is still 28 by 28, it's a uint, and the numpy array contains here. All right, so let's see if we can, for I in range, let's say 3, print I. All right, so what we're gonna do, we're gonna try to, all right, so we can do here plot figure, plot image, show, train images I, color bar, plot read false, plot show. Okay, what are we doing here? So in here, again, this is now too big. What we can see is that we have a set of images that we've rendered from that data set. So these are the 3 first one. And if we print, after showing each of the images, we print the train labels I, we're going to render them again. Is that why? Okay, so yeah, it's here. So you see that this number 9 represents the class to which this belongs to. This is class 0, this is class 0, probably shirts or yeah, something there. So let's take a look at the data here. So once we download that data set, as we said, we have the train images, train labels, test images, test labels, and as we saw there, 28 by 28 numpy arrays. So yeah, you got it there, so I got it right. And here are the classes that each of these images corresponds to. So number 0, to which these two correspond to, are t-shirt top, and number 9 are ankle boots, right? So we have sneaker is 7, so this is ankle boot, something that is something that we can differentiate. So if we do maybe, let's do 100. Let's see if train labels I equals 5. We're doing Python, not C# or JavaScript. I don't need to print the label, but I'm going to show that. So here, we're in a hard way, right? We are only displaying things that belong to the class sandal. So this is number 5, right? So we have here class number 5, and all of these are sandals. The next thing, and this is just to show you how well this data set is labeled, everything that is on this data set is properly labeled. So let me just get maybe less. So we have a few dresses here. So it's class 3. We can see number 5. Well, number 5 was sandal. We can do number 4 coats, and so on and so on. You kind of start getting the hang of this, right? So the next thing that we can see here is that the image color goes from 0 to 255, and actually here we're using the color bar, but if we render it normally, let me see, I think, well, the color bar is just to show that color bar, but if we do the CMap and we use the grayscale one, this is the actual information that we have there. So everything is zeros, which is more efficient, and then the white part is the part where there's information about the image itself, right? Let me just see if I do, let me just see really quickly what happens if I do this. Okay, So yeah, we can invert these images if we, we just get the NumPy array and say, okay, because these are images that go from 0 to 255 numbers, we divide by 255, and then we have this image mapped to 0 to 1. And then if we remove that from 1, we'll invert the image. Something that we could have done also if we did something like this. All right. So you can see now we go from 0 to 255 still, but instead of the color map that we were using before, we are using the gray color map. We can use another color map. There are many, many, many. You can choose, for example, if you do CMap, color map, names, matplotlib. And you can take a look here and you can choose the gamut of colors that you like. HSV, for instance. Let's just try that one, HSV. Right, so, and this is inverted, so maybe let's just leave the image as it is. You see, so this is just to visualize the data that is in there, and you can play a bit more with it, but for now I think we have enough. There's only one bag on the first images. Let's just find more bags. Okay. All right. I'll pause for a second. Is there anyone online that just joined that wants to say hi, where you're connecting from, and what do you think that where you're expecting to get out of these videos? And also let me know if you have any questions. Just type it on the chat and I'll be happy to answer them. All right, let's keep going. So we're gonna take this out now. So we're gonna remove this visualization code. We have 60,000 train images and we have 10,000 test images, and also 10,000 test labels, 60,000 train labels. All right. So actually, if I press Z, I think where was it? To undo set level action, use Control MZ. All right. I just want to get this back in case you want to play with it. I'll just leave this here because I'll upload later the notebook. So I don't know if, yeah, I don't know what I'm doing. Redo, undo. All right. Not really sure if I can recover that, but all right. Well, let's actually, because it's on the video, we can go back later and just get that. Okay. Let's just try something. Can I try something? Let's just try to do something cool. So if I go back to this video and I'm going to make sure that the audio doesn't spill in, just gonna mute this. And this is me some minutes ago. Oh, webcam is blurry. Right. Okay, seems like I'm back. All right, so what I was trying to do here is if we go back to this video when I still had that text written there, so I can do this. Oh. Okay, I can do this, so take a screenshot. And And I'm just, I'm just getting my screenshot here to the desktop. This is just something silly that we showed, I don't know if last week or the other one, but if I had this from a video, and I can just do this. I can go and say, okay, so I use I'm going to use Tesseract and get that image URL, and we're just going to make a file here named code that is going to have the text in this image as editable text. So we can, I don't know if this will work with code that well, but yeah, you see, so I've done OCR, which is actually using machine learning as well on the version 4, I think, and I can paste this code here. And I can reuse this. And not sure if there will be something that doesn't work properly, but this seems to be, this seems to be like really, yeah, exactly. So this seems to be really, really well recognized text by Tesseract, because it's machine written text, and even with a mono font, which is the ideal for a text recognition task. Okay, so we'll leave this here, and what we'll do is something different. So I'm gonna just count here for printed images 0. So printed images +1, and we'll do if printed images is greater than 3, continue. So we're gonna range by 2000. All right. And now, regardless of the class, we're just gonna print 3 images, or how many we want. So if I say here, it doesn't really matter. I could put here 10,000. But if I choose one category here, so number 8, I'm just gonna print 3 images, or how many you want here. So if I say, okay, print 10, that's gonna print 10 images for us from that data set. Okay, so let's leave it at 2 images so we don't clutter the screen, and let's keep going. So we took a look at this classes list, and one thing we need to do is define it. So we're gonna just write here our class names. You will do this for your own data set if you had them, but we have the classes here. So t-shirt top, and I'm just gonna handwrite this so we do everything step by step and understand everything that's going on, and not copy text from the page, because I think writing code helps you interiorize. And again, hello everyone who's connecting online today. I'll invite you to introduce yourself on the chat and let us know who you are, or at least where you're connecting from. All right, we also have coat, we also have sandal, we have shirt, we have sneaker, we have bag, and we have ankle boot. All right. If you're wondering, and if you know some Python, what happens with this comma is that in some languages you cannot write that comma. I think more and more languages are letting us write that comma. And the reason to do that is that if I now add a new item here, so let's say gloves or something, and don't put the comma, right? If I did have my code like this in code versioning system, if I then add this, it's not only that I've added this line, but I've edited this line by adding a comma. So many programming languages let you put that comma there. So if you add a new item, the only thing that will change is the new line, but not the 2 lines, the one above and the one that you've added. All right, so we have this here. So we now have this ankle boot and list here, and all our class names. Let's just make a bit of room here, and we can iterate for class, a class in class name, also for class name in class names, I can print the class name. So we have our list here, and you know, these indices match, so I can do this, and let me see, not can do that, right? All right. Just to make sure this matches, so 0, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. All right, so our classes are good, they match, just making sure that we're not messing it up, and we'll have issues later. And then explore the data. We've already explored the data, so if we do train images.shape, we get that we have 60,000 images of 28 by 28 pixels. If we do test images.shape, we have 10,000 images, 28 by 28 pixels. This is what we're doing here. We can also count it. We can do many things. And you know, if you just print the variables, we'll see that something we saw before. We just have an array, and you know, we haven't done anything to it. We visualized the images already, so we printed them and saw the bar. And what you know the tutorial asks us to do here is format our images and you know, map our images from 0 to 255 to 0 to 1, right? So how can we visualize this? So test, so this is test images, and then we'll have train images. Okay, so if we were to print, you know, right now the images before and after this step, let's just try to do that. So let's just try to say here print train images 1, and we're gonna get only, let's see, all right, just a few numbers, but I don't know if we're gonna get anything useful from there because there are many zeros that are black. Yeah, this is just black color. There's some, you know, there's some numbers. What you can see here is not the variable we had above, is hello Bea. Bea is connecting. And for this, let me just move here. Okay, so let's go back a bit, and now that we're seeing some numbers, what we're gonna do, let me see if I can, okay, so we're getting some numbers here, but if we run the entire notebook again, we're gonna see these numbers change. You see everything is from 0 to 1, but if I run the entire notebook again, and this is probably gonna download the data set, well, it doesn't because it knows it's there already. So now the numbers are integers and go from 0 to 255. But if we print this statement right after doing this, we can see that it's been mapped from 0 to 1, right? And I'll zoom in so you can see. So the last numbers, for instance, here we have 40, 61, 44. And if I go here, 40, 61, 44, and I don't know which ones are those, but you know, if I do 40 divided 255, yeah, I get that number. So 40 divided to 55 is 0.1568627,451. And this is being rounded. 1, 2, 3, 4, 5, 6, 7, 8. Probably float 8. Float 8? I'm not sure. All right, so we have that here. And what we want to do now is make sure, well, we can keep going, right? So I'm going to remove these from here. This is just to visualize that our data is working. We're going to delete this, and we're going to delete this. So we have our data has been formatted, and we're going to continue. So, well, we've already done this. They're just doing it in a fancier way to build a table. So we can plug here, make a new figure. All right, and we're gonna add things to this figure. So before, we were going through many things and just selecting everything that belonged to a specific category. But right now we're just gonna print everything. We're gonna make a table. We're gonna print everything, like you can see here, and we're gonna render the image and the label that image belongs to. So I didn't comment on the PLT library. So above here we have matplotlib pyplot as PLT. This is a library that allows you to do this that we're doing. Not only print images but also put the axis here, put the color map or the color bar. Is it color bar? Yeah, the color bar. And do things like building grids of images and inspect information that we have as images, as tables and other data. And this is also for data science. You can build tables, you can build charts, and many things that we'll do today as well. So here we're creating a figure. So the figure size is defined here, 10 by 10. I don't exactly know what these units are, but maybe we can get some information here. So there is a nice autocomplete in Google Colab. So we get here information. So we get the fixed size, and if we look here, the fixed size is optional, none, with height in inches. I don't know how the inches translate to my computer, but I know more about centimeters. So let's just use that. And 10 by 10. Subplot is to make one of these boxes, and the X ticks, we don't want them. We don't want the Y ticks either, so that's to remove let's leave this out for a second. The grid, let's leave this on true for now. And image show, train images, exactly the same that I was doing before. CMap, plotlib, CM binary, and X label, class names, train labels, Y. All right, PLT show. So invalid syntax. All right. So it's gonna print our table, and you can see why they were adding some of those information here, some of those commands. So the grid, we don't want it, and we want to hide the ticks. The ticks are those Y and X axes. And this is your image. It's exactly the same because we're using the same data set. Let's see if we can do something different. So we have an empty table there. Let me just do this here. Not remembering. All right, don't remember how this function worked. Start, stop, step. So 10, 20, and 1. All right, so we can actually move. So if we do 11, they will probably slide, which is cool. So 11, 12. All right. Let's just make something here just to play a bit with this. So if we do this, for example, start is 10 and amount is, so this is 10. So we have here start and then start plus amount. And if we move 1, we're sliding to the side. Why is that doing that and not just showing I? Oh, I see. I don't know if you see what I'm doing, but I'm just trying to make a quick animation. So okay, let's start at 0, and let's start saving these things here. I'm just gonna make a quick animation. GIF, fashion, MNIST. We're gonna make an animation. We'll share this later online on social media as the cover of this tutorial. Maybe if I do this bigger, I get more resolution. These images are still not too big. All right, so let's keep it at 15. Okay, so let's put this here. Okay, so I saved that one, and now I do this. Would be better if we could download the images and automate this, and I like that. So I'm going to go to video here. All right, let's just take some code from here. All right, so what we want to do is, every time if I do this, just look at this shirt. If I do that, the images are sliding or not. Maybe this is not working. Yeah, 3, 4. Yeah, so the images are sliding to the left. So what we're gonna do is that we want to iterate through this. So we want to make, so for these to get out would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So for I in range 11, right? So, or maybe 10, from 0 to 10, yeah. And then we'll do a figure. We'll do all these steps. And then for each of these, we're gonna save the image. So let's just do 2. So plt save matplotlib save image, save fig. So it's gonna be J and J, and we're gonna do haha. Right, anybody? Let me see. So I think this is what I was looking for. Right. Yeah, let's see what this does. Okay, so what we have here, we've generated 2 images. They don't slide because I need to make the start slide. So I'm gonna put this here. Right, so they're sliding to the left. I don't know if you can see it, but they're going that way and then going to the upper row when they finish. So now we've saved both frames. I'm not sure if this is actually saving anything. Not saving anything. Name. Maybe I have to save before showing it. Yay. Okay, and then save without margins, but inches to 0. bounding box inches. But inches. Okay, we're not gonna care about that. All right, so we can now, after we save, so what we were looking in this video is that I can import from Google Colab, import files. So this is to download an image, and then after we save it, we're gonna do files, download, and this is the name of the image. So figure name. All right, and then we download it, and that should download it to our machine. So cannot find that name. All right, so we will probably just put PNG here. downloading, and we got them. Yeah, I don't know why. Yeah, so this image is bigger because we've reserved space for that. So we have 15 by 15. So we're saying I have a 5 by 5 where this is actually a 5 by 2 maybe. Oh, 2 and 5 maybe. Yeah, I'm not sure what this is doing with the margins. To fixed size. Maybe this is 10 by 10. Well, I'm not sure what that's doing. Right, like that better. And oh, tight. Yeah, that was the option I was looking for. So here I'm just gonna put bit boxes tight, and hopefully that gives us a tight image. All right, that's exactly what I wanted. Okay, so now we're saving images. Don't close that. We go to our downloads and here. All right, so let me just put this, make this a bit bigger. I'm not sure. Yeah. All right, so once I do that, so we said we needed 10 steps here that are actually, so 11 steps are actually from 0 to 10. So now we're gonna do that. And you know, we're here in between doing the machine learning tutorial, but let's just make a GIF. So we use this for social media, so we can share that. And you know, this is also good. So when you have machine learning models, a really important part, at least for what I see, is sharing those models or the findings that you've done. So being able to manipulate the data and create graphics that are appealing and that communicate what you've been working on are pretty good. All right, so let me just see here. All right. Okay, so let's see what we have. All right, and now we just need to see if we get the effect that we wanted. Frames 0, 1. Okay, so here we have this folder, we have all the frames. So I'm gonna make a quick make file to make a GIF. All the images in frames 0, 1 are PNG. and the GIF is going to be called GIF fashion MNIST. The GIF. Nothing else really. Make GIF. Now this is going to create an animation for us. Good, not bad. So, and I'm using image magic to make this GIF. So I could, I could specify here the delay. Delay. Let me just try one thing. Okay, let's just put here delay and delay. So make GIF delay. Right, make a faster GIF. Yeah, I'm not sure if you can see that it's actually sliding. Maybe, if we just have one row, it's a bit more understandable. If we just have one row of GIFs instead of two. So for that, we'll just do 5 of this. You see, but now we've automated this, so we could, we could even install image magic on here. So we could do, I don't know if we could do that. Yeah, I think we could, but let's not do that right now. All right, so we have the frames here. So frames, 5 frames, and for this, we're just gonna copy here. Give 5x. All right, only thing we gotta put here, a 5. All right, so engineering architecture says, "Hi Nono, what's a good rule of thumb for number of training data images for Stylegun 2? Well, as far as I've seen, at least the runway tutorials and some information I've seen out there recommends from 500 to 5,000 to be on the safe zone, to have something that works. But you probably have to go up to 10,000 if you want to start having something good working. If we look at this data set, so the cartoons data set, it seems like it would perform really well. It has 10,000 images. So it has 10,000 PNGs and 10,000 CSVs that have some metadata or labels of each of the images, but that is not used to train Stylegun with this data set. So I would say when you start having 500 images and more, it will start performing properly. But with less than maybe 200 or 300, I don't think there will be good results. But yeah, I'm still to try. I'm trying to prepare more than 5 images of my sketches dataset to train Stylegun with. Have you tried training Stylegun with any datasets? All right, let's see. And thanks for the question. So I'll answer here in case some people look at the chat. I would say from 500, I need to be on the safe zone, but 10,000 plus would perform the best. All right, so it seems like something got misformatted here. So let's just do that, run this again. All right. Okay, so we have this GIF. Like now, if you see it in small, you probably can see that it's sliding. All right, cool. So that's that. So we've looked at the data, and we have a good hold of how can we label it and understand a bit more about the fashion MNIST dataset. And now we have to build the model. So we're up at 1 hour and 20 minutes. Wow, time flies here. All right, I see that new people are connecting. Hello. And I would invite you to ask questions or to tell us who you are and where you're connecting from. Right now, what we're doing is that we've looked a bit about we've understood a bit the fashion MNIST dataset, how to load it, how to look at its data, how to visualize the images, how to look at the labels, how to even create an animation that shows many of those. And now we're going to build the model. So we're going to build a neural network that requires, well, just a sample convolutional neural network. No, actually, just a sample sequential model, not even a convolutional neural network, to train with this data set, right? So let's get started with that. And if you have any questions, put it on the chat. Okay, so here, you know, the syntax that is being used here is TF-Keras sequential, right? And then there is an array here. So if we look here, groups a linear stack of layers into a TF-Keras model. The sequential provides training and inference features on this model, right? So there's layers and there's name. The name is optional and the layers are optional as well. So we could say, okay, this is my model. We could print a model summary, and then, you know, the model has not yet been built. Build the model first by calling build or calling fit with some data or specify input shade argument, blah, blah, blah. So there is some requirements. There are some requirements before we can get started with looking at a model, because the model is still empty. It doesn't really have anything. So the first thing we can do here is we can add some layers. So let's just put here build the model, and the first layer we can put is TF-Keras layers, flatten, input shape, and the input shape is 28 by 28. And that's it. And now we get the model summary. So the input shape is 28 by 28. That is 784. That's a flattened layer that just gets all the pixels in a 1D array. And we can, you know, we can pass, I don't know if we can pass something through this model yet, but we definitely need to compile it. So I don't know if we can do model predict train images 0. Yeah, okay. So what model was constructed with shape for input tensor, blah, 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 but it was called input with incompatible shape, non-28. So for this, we actually need to do maybe expand them. Was it 0? Sure. Right, that seems like it works. So what happens here, so we understand what we're doing. The code here, so when we have one of the train images, so we have the first one, so we could say before shape, so it's 28 by 28 array, which is at the end of the day similar to if it was a TensorFlow tensor. And if we expand the dimensions and look at the shape again, you know, we're getting tensor shape is now 1, 28, 28. That means that this is a batch. This is like a batch of images, and we have you know, we have just one element on this batch, but we could have multiple. We could do probably we could do something like a vertical stack. So we could say, let me see if I can do just a test here. Okay, yeah, so we're stacking tensors, in this case 2, 1. We have 2 elements with size 1 in this stack of tensors, right? And this is what we could use to create a batch manually. So we could do train images 0 and train images 1. So we'll get the first 2 images in our new tensor. All right. So yeah, so we have a batch, 2 items that have 28 by 28 pixels, and we can do this with this as well, so expanding the dimensions. But we can use this TF stack, so we could pass this batch with 2 tensors so 2 images to predict, right? So we're getting 2 output predictions here, but at the end of the day they're just I believe so what we're getting out of this model.predict is that we initially have a batch of 2 items but 28 by 28, and we might get a batch of 2 items that are 668, right? So we said 784, sorry. So we say that this is our output. Then we get the output shape. Oh wait, we gotta first run this block and then this one. You see, so we have a tensor that is has 2 items that are 784, and those values are just gonna be the same values on the pixel of an image, but in a row. So they'll be like all the pixels continuous after the other. So let's see. Not sure what I'm doing. TensorFlow stack image 1D tensor. Yeah, so this is what happens when you stack the values. I'm not sure what representation we can get here that is good. Tensor 2D to 1D. I don't have my iPad on right now, but it's just going from something that has like rows and columns to just a single row. And okay, so here we're getting comment from engineering architecture. Gotcha. Thanks, Nono. Yes, I have trained a Stylegun model on building floor plans around 1000 images. The results were satisfactory, but when I did the same on section images, which was around 300 images, it looked like the model failed. Yeah, that's exactly what I thought that would happen from what I've looked at. Yeah, feel free if you want to share your results with the building floor plans here. We'll be glad to open it and take a look. All right, 1 hour and a half. So we have 30 more minutes or so. So let's just build the model as this says. So what we learned right now, we can stack multiple. So let's say here we're stack images in batch tensor. So multiple 28 by 28 images in a stack that gives us a shape of non 28 28. None means, it is the batch. So the batch, right now here, the shape of our input is actually non-2828. And I believe this should work as well if we just explicitly set that non, yeah, probably not. Let's just leave that as it was, put our summary. But what we have to do now is actually build the model. So this model is a fairly simple model, has 3 layers. So we have this one, we have the Keras layers dense, 128 activation function ReLU, and TF Keras layers dense 10 units. All right, so we have our model. Now our model goes from 784 to 128 activation map, and then dense, which is just getting 10 classes, the 10 output classes that we're looking for. All right, it's a fairly small model and already has 101,000 parameters that are trainable. All right, so we have our model. We can still feed our images, so we can still feed the same sort of images. We can do it this way or the other way. We'll leave this here, and then we have our output. This now takes a bit longer, and now our output shape is 210, right? So every time we pass that through the model, now if we print the output, what we have is 2 different arrays with numbers of how much it thinks, or how much the network thinks that each of the classes is activated. So right now this doesn't make any sense because we haven't trained the model. And yeah, so Mayur, you're not disturbing at all. So this is an interactive thing, and if you want to comment, and we can have a conversation. So this is not something that I'm recording to later share or clean up or anything. So feel free to ask questions on the chat and keep the conversation going. I'm fine with that. All right, so let's see. And I know Majur from online, but he's also on the Discord channel, so we can continue this conversation as well, the machine learning channel, if you want to post more stuff or share your projects. All right, so the first layer in the network, let's read this. Let's just take a deep look at this and learn a bit more about what this network is trying to do. Oh, that's for later or some other time. So build the model. So the basic building block of a neural network is the layer. Layers extract representations from the data fed into them. Hopefully these representations are meaningful for the problem at hand. Most deep learning consists of chaining together simple layers. Most layers, such as TF Keras layers dense, have parameters that are learned during training. We've set these layers as the layers of our model here. Oh, not here, here. And the first layer in the network, the flattened layer, transforms the format of the images from a 2-dimensional array of 28 by 28 pixels to a 1-dimensional array of 28 by 28 that is 784 pixels. That's a 1-dimension array, a really long array of numbers, one after the other. Think of this layer as stacking rows of pixels, what I mentioned before, so each of the rows and lining them up in a single vector. This layer has no parameters to learn, it only reformats our data. After the pixels are flattened, the network consists of a sequence of 2 TF Keras layers dense layers. These are densely connected or fully connected neural layers. The first dense has 128 nodes or neurons. The second and last layer returns a logits array with a length of 10. Each node contains a score that indicates the current image belongs to one of the 10 classes. Alright, so compile the model. Before the model is ready for training, it needs a few more settings. These are added during the model's compile step. The loss function, the optimizer, and the metrics. But what are these things? Really, what are these things? So the loss function measures how accurate the model is during training. You want to minimize the function to steer, so move the model in the right direction. So this is, you compute, you have a function, there are some standard functions, but there are some functions that allow you to measure how good or bad the model is performing on the data that you have, right? And over the training steps, the model is going to come to that loss function and compute how accurate it is in calculating whether the data belongs to the right class or if it's failing. The optimizer is how the model updates based on the data it sees and its loss function. So this is a behavior that lets the model know how to optimize. So what change to make on the model to test to see if it's improving, right? And then the metrics. So used to monitor the training and testing steps. The following example is accuracy. The fraction of the images are correctly classified. You can measure loss over time, you can measure accuracy, and there are other measures depending on the loss functions that you have and the settings of your network and the nature of the network that will be helpful to measure over time. If we scroll or forward to the future, right, there are these, and sorry for moving these fast. Let me just see if we can maybe just do like this. So they don't show it here. They don't show those charts here that usually you show the chart where you see the accuracy over time. Okay, I see here Pedro Cortez. Thanks a lot for joining us, and thank you for being there. If you have any questions, feel free to drop them in the chat and let us know, or also let us know where you're connecting from and what you're expecting to get out of this. I think, if I don't remember wrong, I've seen you on the live stream before, right? All right. So let's write this. So we have our model compiled, so we have to specify optimizer, loss function, and metrics. So we now jump to our other window. So we do here, we have our model that is already defined. So we're gonna do model compile, and we have to do three things: optimizer, loss, and metrics. All right, so the optimizer is Adam. So, we're not going to spend time right now, but we'll do in the future. So Adam optimizer is one of the most famous and most used adaptive learning rate optimization. So the learning rate is not fixed across the whole training, but it's adapted. Maybe it has a bigger learning rate at the beginning, but then it decreases later at the end as it's getting better and better. All right, so the loss function, so we're going to use the sparse categorical cross entropy. Let's see if we get, let me just close these things. What else we have here? Nothing. All right, so I hate this. All right, let's actually just put this here and put this here. So TF, keras, losses, sparse, and I can click an autocomplete, but I'm gonna write it sparse categorical cross entropy from logits true. All right. Oh, all right. And then the metrics are accuracy. All right, so let me just format this a bit better. Can we use night mode here? Dark mode. Ooh, adaptive. Okay. Yes. Okay, so we now have the model, so let's play it. The model summary. Let's see if we get any information from that. Sequential, flat and dense. Yeah, we don't really get any information of that, but these things that you compiled here, if you save the model, they will be saved as well. So that information will be saved there. and will be, you will be able to load the model, and these parameters will stay there. All right, and train the model. All right, so now to train the neural network, we just have to do a few steps. We just need to feed the data of the images on the training set and the data of the labels for the training labels. So it's like saying, okay, I have 60,000 images and 60,000 labels that match those images. And the model needs to learn that relationship and then adjust the weights in these 101,000 parameters, right? The model learns to associate images and labels. You ask the model to make predictions about a test set, in this example a test images array, and verify that the predictions match the labels from the test labels array. Depending on the accuracy, so for example if we get 80% accuracy, it means that the model will classify correctly 8 out of each 10 images. Alright, feed the model. Feed the training data, and this is what we're gonna do, right? Feed the model. I don't know if this is feed or fit, but yeah, feed the model. To start training, call the model fit method. So called because it feeds the model to the training data. Right. Yeah, so what are some, I'm reading here from the chat, so let me just bring it here. So I don't know if I can zoom in. What are some ways one can ensure that training data is not biased? It's well distributed and avoid outliers. One technique I used was image TSNE. Curious to know your thoughts. Well, image TSNE can help you understand the different types of data that your dataset has and visualize it, and then see that is evenly distributed according to the relationships of the data in that training set. But for not biasing the data, I mean, one of the things is you have to have the same or similar amount of images per class. So if we have 60,000 images and we have 6 classes, we want to have 10,000 images approximately per class. But this is not always true. Some objects might be harder to recognize and might require more images. And also, when you say avoid outliers, I guess, I mean, there are some techniques like activation maps and the confusion matrix. So the confusion matrix would probably be what you want to do to avoid outliers or things that are not being categorized properly. Those include false positives and false negatives, right? And true positives and true negatives. So that is the confusion matrix. This is, let's say, what is this? So let's put here responses at 144 or something. I don't know. I would say confusion matrix, activation maps, even labels per category. But yeah, so the confusion matrix lets you have a sense of what things are being classified properly and which ones are not. So let's see on MNIST. So for example, in here, what this image represents is the things on the identities, right, on the mid diagonal, means that 0 was classified as 0, 1 as 1, 2 as 2, and so on and so on. If there were colors outside of that matrix, so if there were colors below here or above here, that will mean that those got misclassified, and it will the confusion matrix will tell you with which other classes are getting confused, right? That is because sometimes number 6 and 8 might be really similar and be misclassified. So here you can see an example, even though it's classifying really, really well. For instance, here shirt and t-shirt is getting confused, coat and shirt are getting confused. Things that make sense that maybe will get confused, but some others might not make so much sense. And you can identify patterns like that. We've identified patterns at work where, you know, you can see exactly what symbols are being confused to which symbols. And then you can go into the data set and say, oh, there were actually symbols that were misclassified. Or you can see, okay, these types of data are really similar. We need to actually add more samples of real data. So the machine learning model learns from those differences. All right, thanks for that question. That's a really good question for right now. All right, so easy here, right? So model fit, train images, train labels, epoch. So it's really straightforward here. So what we're doing is that we have this model and we just do model fit, train images, train labels, and epochs. So I'm just gonna do 2 epochs right now, really quickly. So we have a GPU and this runs really fast. If we didn't have a GPU, it would probably go slower. We can try that on my machine to see the difference. So we have these 2. How we can do that is we just go here, we download the notebook, and I'm gonna open this with Visual Studio Code. So there's nothing to open this with. All right. Code that. All right. So I have the Visual Studio Code extension for the Jupyter notebooks to run. I think this is just installing the Python extension, and this means that I can simply drag and drop or open a notebook in here and run it if you have the right environment to run it with. All right, and this is opening now. So I'm not gonna go into more detail on how you get to run that, but I do have a video I've made before that you can watch on the YouTube channel that talks about how to set up your environment. So if you go here, this video actually tells you about how to set your custom Python environments with Anaconda and use them in Jupyter notebooks. This is exactly what we want to do right now. So Mayur, does that help? Do you think that's helpful? Do you think that is that the type of answer that you were looking for? All right, so we have the same notebook here, and I'm just gonna go for my TensorFlow 2.3.1 runtime. I'm gonna zoom in here a bit, and I'm going to move to the right, and I'm gonna run this. So if we run the first one, so if we run the first cell, this kernel hopefully has our TensorFlow 2.3.1 version. I'm not sure if I had them properly set on my machine. Let's just try to do that. And again, what we're trying to do right now is try to see if the training here is a lot slower than on the cloud, because on the cloud, Google Colab is giving us a GPU on the back end of the notebook for free. And you know, this cell is low because we just started, so no matplotlib. All right, so we will do this here. So we're gonna do pip install. Well, this is a bit dangerous. So if let me just do which pip to see what pip we're using. Anaconda Beam. So this is not exactly what we want to do. Python. Let me see, how were we doing this? Conda activate TF 2.3.1. Okay, and which Python 3? Okay, this is the Python that I want to use, and this is the pip that I want to use, right? Yeah. So pip install matplotlib. Hopefully this installs it into the kernel that I need it to be. I mean, the video explains it, and running Colab script locally. Oh, I didn't know that. I'm gonna take a look at that right now. So Mayur, so okay, so we have this installed here. I didn't know. So Mayur is commenting that you can run the Colab scripts directly locally from Google Colab, or that's what I'm understanding. So if I run this now, hopefully our runtime already has matplotlib, because I just installed it, and we're gonna see it in a second. But this is especially slow right now, and I don't know why. Okay, run. Yeah, I don't know. I cannot see an option to run this locally, and maybe, oh, connect to local runtime. All right, nice. Okay, we're gonna try that. All right, so but my local environment is working here, so I'm gonna download the MNIST dataset, which is pretty fast. We're gonna verify that we have the dataset downloaded, 10,000 images. We're gonna render our images here. We're gonna load or create our class names. We're gonna see the shapes. This works exactly the same. We're not gonna run this one because we don't have Google Colab in here, and we're going to create our model, get our model summary, and see the training images here, stack it. We're gonna predict and see that we're getting the right output, get the model. We're going to compile the model, get the summary again, and then train. It was taking 3 seconds on the cloud, and it might be taking the same here. I'm not sure. Huh. All right, so this is actually not really taking that much time. 4 seconds against 3 seconds. All right. All right, so we're gonna reinitialize everything. So we're gonna run everything except for the GIF generation code. All right, so we're going to, how can I restart the kernel here? Terminate. Yes. Runtime disconnected. All right, so we have here GPU, and we are going to reconnect. So reconnecting means we're getting a new kernel, so no variables are allocated. So if I click, the file system might stay the same. Nope, we wiped everything out. All right, and if we try to run the cell, it fails because we haven't, nothing has run really here. So we're just gonna run everything, but we're gonna make sure that we have this at 10 epochs. All right, so we're just gonna run everything, and this is gonna be really, really fast. All right, so we're training. So once we train, we'll have a model that will actually do predictions that make sense. This is, if you think about it, is super easy. We have only 3 blocks of code that we have to set up to be able to train an image classifier. And the most important thing here, even though, TensorFlow library, Keras, the algorithms, the optimizer, all that stuff is really important. But the most important thing here for us to be able to train a different data set is having that data that is super, super, super well labeled. Not only for the labels themselves, so the number that corresponds to each of the classes, but for the formatting of those images. Those images are all from 0 to 255, integer format, 28 by 28. All the the pictures are taken on the same angle, the same normalized coordinates on the center. It's a really, really regular data set. All right, so our model has been trained now, and you're going to excuse me for a second because I'm gonna go and grab some water. Oh, I'm blurry. Okay guys, if I'm blurry, let me know, because that really bothers me later, seeing that the webcam autofocus failed and I got blurry. All right, so I'm back at not blurriness. All right, let me drink some water and I'll be back in just a second. All right, and well, before I go, let me just open Repost Live. Okay, what is this? Let's put this here. All right, be back in a second. Okay, I'm back here. So before we get started again, I want to say hi to everyone who's online again. So I encourage you to tell us where you're connecting from, at what you're looking out from getting from this machine learning series, and what you would like to see in future live streams. We're gonna be going for many weeks, hopefully, and I would like to know what should I cover in next videos. This is an exercise that I'm trying to do to reinforce this knowledge and to, you know, demystify how hard some of these things are. All right, so we're back here. So we have fitted our model. So we did fit our model, and we have a fit model here. So the first thing we're gonna do, we're gonna try to play with it. So we're gonna try now. So before, we were getting the output from these two images, right? So we can do exactly the same thing and see that output and compare it. So new output. So let's say output v2, for instance, and just output it here, and then output the other one here. So what you can see here, once we pass these two images through the network, we can see that the data here, what we can see, I don't know, try to see what's going on in here. So from the output v2 that is with the model trained, and this is with the model untrained, what we can see is that for the first image, the highest number is this one, is number 9. And for the second one is 8, right? We didn't really see any patterns like this here, but we can clearly see them here. So if we look at the first and the second images, so this is, and you know, instead of doing it by hand, well, let's do it by hand first. So this is 9, which is 1, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, actually. So that's the last class, and then this one is 0, 1, 2, 3, 4, 5, 6. So we have the last one and then 6. If we go into the tutorial, right? The thing that I'm gonna look for here is this and this. So it's ankle boot and t-shirt. And I think I got the two first images, and that those are the two first images. So if we go back here, we look at ankle boot. So number 9 is ankle boot. And the other one was 1, 2, 3, 4, 5, 6. Sandal or shirt. I'm not sure. I think it's shirt, right? So shirt. Yeah, shirt, right? So we trained that model really quickly, and we were able to see that, you know, if you see 0, 1, 2, 3, 4, 5, 6, it's a shirt. So the model already classifies properly. What we need to do now is to measure that accuracy and try to plot the results. So if we take a look in here, if we look at model.fit, that is where we were before, we can scroll up and and see that. Let me just take this out. To gain more space. So the model takes the same to train. As the model trained, the loss and accuracy metrics are displayed. This model reaches an accuracy of about 91%. So we can go back to our training, and here on accuracy, you see 91%, and the loss goes down up to 0.23. That means that the model is really accurate at classifying our images. Next, compare how the image model performs on the test dataset. Right? What we've done right now is that we've tested the model with two images that were on the training dataset, but not on the test dataset. So if we do test images and we get two images from there, we see that it's also telling us, okay, this is highly probable that is an ankle boot, and then for the other one is probable that is not sure what that class was, but you can take a look here. A pullover. All right, so let's evaluate the model. So let's just put these side by side again, so we are able to read a bit better. So so here, test loss and test accuracy, model evaluate, test images, test labels, verbose 2, and then print test accuracy equals test accuracy. Right, 88%. I'm not sure why mine shows higher, but you know, it does. I'm not sure what I did wrong or right. All right. So I see some questions, and I'm gonna address them as we come to a close, but for now I'm just gonna keep going. So it turns out that the accuracy in the test data set is a little less than the accuracy on the training set. This gap between training accuracy and test accuracy represents overfitting. Overfitting happens when a machine learning model performs worse on new, previously unseen inputs than it does on the training set. An overfitted model memorizes the noise and details in the training data set to a point where it negatively impacts the performance of the model on the new data. For more information, go here and here. So demonstrate overfitting, strategies to prevent overfitting. And this is something that, you know, is good to prevent overfitting. So those are the layers that we were talking about before, are good techniques. Make predictions. Okay, this is what we wanted to do before. So before we were getting the logits, right? We were getting the logits function here, where we had to convert that to a number or look at the index. But let's actually get the probability model. This is something that what we just do is we're going to attach probability. We're going to, and give me 1 second. Yeah, thanks, Mayor. I'll be back. I'm gonna take a brief break, and I'll be back to wrap up in a few seconds. All right, let's wrap this up. So I think we'll continue with this one. I'm enjoying this tutorial today, so we'll continue with this one next week and continue where we left it. Sequential model, and the last thing that we're gonna do today, there are more things that we can do to look at how the network is performing. And I don't know why my camera keeps on focusing. All right, probably just disable the autofocus. Thanks to Mayor for letting me know that. All right, so the last thing we do here is that we create a new model by stacking our train model, so the model that we have up top, and the a TF Keras layer softmax layers, right? Groups a linear stack of layers into a Keras model, sequential, blah blah blah. Okay, what's this? Let me just take a look. Softmax activation function, right? And this just tries to get the number that is getting activated in each of the outputs. So we're gonna define that new model. We can do probability model.summary, and now we can see that we've attached that sequential model that we had before and then this softmax. And we still get 10 outputs, but we'll see how those change. So now we do we get predictions, so probability model, predict, test images, but we're not gonna do that yet. We're gonna get the same, so let me just zoom in here. We're gonna get the same exact data that we were using before in this one. So we have this stack, just 2 images. Actually, let's just take a look if we can just do this. So we do test images shape. Yeah, so we can simply do this, right? Just get 2. So we don't really have to stack them manually. All right, so we'll just get the 2 first test images here, and logits would be to predict the same with the test images. All right, so we print the logits and we print the predictions, right? So there's a softmax function, and what we can see here, so here the number 3 is the highest number, and I believe here this one is the highest number. So yeah, there's some magic going on there that I can't right now explain. Hey, I can see Love just connected. Nice to see you guys around here. I don't know if you saw the video from last week where we shared some of the tests that I've been doing training classifiers with my sketches and Love. All right, so yeah, this is a simple example and that we're almost wrapping up. So let's just take a look here at those predictions, right? So a prediction is an array of 10 numbers, and if we just get the argmax of the prediction, so we just say okay, so just argmax predictions 0 for the first one, we get 9, right? So it's the same that we were getting before. So we get that that's the class that belongs to that one test label, and in the test labels we can see that that's exactly what we were meant to get. Hey Jake, okay, so for those who don't, I'll just give a quick shout out at Lobe AI that we saw 2 weeks ago. So Jake is here with us right now. So he just connected online to the live stream. So Lobe AI is a tool that Microsoft have put together. They acquired it at the end of 2018, and for 2 years they've been developing it in-house. So I connected with Jake through Adam Menges a few months ago and got to test the private beta. If you go to the tour, you're gonna be able to see a video. Let me see if we can.
Hey, I'm Jake.
A video from Jake, who's connected with us today, I believe, and you can see him explain some of the things that you can do with Love. In this case, to train a machine learning model that can be used with an application on your computer to measure how much water you're drinking daily. And I'll just point you to 2 things, so things that we've seen before on the live stream. So the first one is the actual live stream of that day. So that's live stream number 4, where we talk about, let me just mute this. So we talk about Lobe. So we explain a bit conceptually what Lobe is, and then we go in depth into training different classifiers. I build one classifier with images from my webcam that I think I built the dataset unsuccessfully and didn't work properly. But then I built this other classifier. Let me see if I can find this image here. So this classifier was differentiating between sketches that had color and sketches that were black and white. And yeah, I'll recommend you to go and watch that video if you want to learn how to train your own machine learning models with Lobe that you can then later export into TensorFlow Lite. You can export to TensorFlow Core. You can run as an HTTP server on your machine and stuff. And again, I have mentioned this a couple of weeks now. Adam Menges, one of the co-founders that has been developing Lobe with Microsoft in-house for the past 2 years. You should go and give the interview that we did together a listen. So that's a shorthand at gettingsimple.com/Adam. So if you go there, you're going to be able to hear from one of the co-founders. How was the experience creating the product, startup, the acquisition, and many other things. Yeah, I mean, there's nothing crazy there, Jake, that you don't know, but maybe you can skim through the video and see. Maybe you can give me some hints on how to make that better. And if you haven't listened to this interview with Adam Menges, that's been, you've been developing the product with him, I will encourage you to give it a listen. I edited it with a lot of love, I would say, and it's also, there are like detailed episode notes and a transcript that I have to release, by the way. But yeah, all right. Thanks a lot for joining, Jake. It's really nice to see you around here. All right, so the thing here, we're not going to follow right now, but if we see what we're going to see next week, we're just going to continue how to measure or visualize the output that we're getting from this test data set of what we've covered today. What you can see here is that from that new network that gives us the probabilities, we can see how probable it is for each of these images to be each of the classes. So I would imagine that, if we just multiply this in here, so if we just multiply the predictions, let me see if I can, let's say, multiply the predictions by 100 plus 1. Wait 1 second. Yeah, I don't know why this doesn't show us normal numbers, but I think okay, let's leave it here. But yeah, okay, so we'll continue inspecting the model and seeing, but today what we just saw is like a step-by-step trying to understand everything in this amazing tutorial that the TensorFlow guys have put together, understanding how to train a machine learning model, so a neural network that only has 3 layers, and the softmax layer, so 4 layers total, takes to train less than a minute, so just 3 seconds by 10, so 30 seconds or so in a GPU, and just a few more seconds without GPU. And I think it's impressive. Again, I'll reiterate, you need 60,000 really well labeled images for this to work. And that's, that's something that we'll have a really hard time doing with our own data, because it's really hard to create a custom data set with so many labeled images so well regularized. And I would say this is it. So for Mayur, for your questions, if you want to put them maybe on the Discord channel, I'll encourage everyone to join the Discord channel. So join the community on Discord at none.mat/Discord, or the link that is on the description of this video. And I'll share. Okay, let's do one thing really quickly. Let's do one thing that I never do. So let's go to that. Let's go to the Colab notebook and let's open that one. And I'll put the link to this on the Discord channel, so you can change to anyone with the link, can view. And I'm gonna paste that right now into the Discord channel. So links for live 6. All right, and I just put the Colab link here on the Discord channel, so you can go and see them. I just see here that Jake just joined. Nice, thanks for joining. Welcome to the community. And wrapping up, so let me just continue here. So we have, let me pop out the chat. I think for building a model from scratch or using a trained model, well, maybe the opposite question. You use a trained model when there is a model that has been trained for hours, days, weeks, or even months in like a GPU farm or something, that has been able to learn a lot of feature extraction, so a lot of features from images. These are networks like Inception or Stylegun or things like this. Stylegun takes months, I think, or days to train up to the checkpoint that they have with the flicker faces in high quality. You can retrain that in a few hours with really, really good behavior, because the first steps in learning and adjusting the weights already were done and work with any images, and then the model gets adjusted. So you train from scratch when you want those base features, the features that the model learns from 0 to whatever you get a good performance, to be of a type that you want, right? The type of data that you need to use. But for image feature extraction, it's something that you can transfer from one domain to the other. So recognizing images of faces might be a slightly similar task as recognizing animals or shapes or other things. So you train and then can do transfer learning just to adjust the weights to a new data set, but the feature extraction layers maybe are not even retrained and stay the same. Mayur from Urbana, Illinois, interesting to know and learn your approach to deploy models. I'm personally interested in learning how to deploy SketchRNN and couldn't find any tutorials. So let us know, Mayur, if you want to deploy SketchRNN to TensorFlow.js, or if it's to the cloud, or how do you want to run it. And yeah, thanks so much, everyone. So I'll just thank everyone who connected today. I'll remember you that the community is interdisciplinary, so we're doing expert interviews and interviews with different people on the Getting Simple podcast. My sketches online that have to do, many of the latest posts have to do with writings about automation and how we live our lives. The YouTube channel, so many of the videos on Python, machine learning, and things as awesome as Lobe and Runway and many other technologies are on the YouTube channel. You can go to that at this URL or at nono.ma/YouTube. And lastly, but not least, I'll just open call to action for those who end up watching the video. And let me see where this is. Machine learning series. And one last chance, if you're connecting live or if you're connecting later, I would really encourage you to leave a comment. So let us know what you liked about this video, what you like about the series, what you like to see in the future. And lastly, let me show you just a note that as many of the other live streams we've done, this video was part of the machine learning series. If you enjoy this content and this is the type of content you'd like to see in the future on the channel, please go ahead and click that button, like the video, because this way I know which are the videos that you're liking the most and you would like to see more of. And it also helps if you subscribe and click on the bell to be notified the next time I go live, or when I schedule live streams, or when I upload new videos. Thanks so much for watching. Thanks for being there. I welcome Jake and Peter and Pedro Cortez, right? And Mayur, everyone. Thanks a lot for connecting and tuning in. For those who didn't hear before, you can join us. You can join the conversation, join the community at nono.ma/Discord. I'm looking forward to hearing from you. And yeah, let us know where you're coming from, what you're looking from in this community. And also share your projects. Let us know who you are and ask questions. Thanks a lot. And I think that's it for me. Have a nice evening, day, or whatever you are.